Physics Lab 1 of objects moving constant speed in the same direction. The purpose of this lab is to take real-life moving objects that are moving in a constant velocity and then take the average velocity, which is the same the entire time, and compute its position and then compare its predicted position versus its actual position. This uses Newton's second law, F equals ma, because as velocity stays constant the entire time, acceleration, which is change in velocity, is zero. Therefore, F net is also zero. In this lab, both the real-life graphed data and the computed graphed data were linear and had identical slopes, so the overall lab was successful. For this lab, we took a rolling circular wire holder thing and rolled it down a table with 2 meter sticks next to it in order to record how far it went, and then based off the video we recorded how long it took and then inserted it into tracker software in order to track its exact position at different times and find the average velocity. This is the graph that we created, with the orange being the data we collected and the blue being the data that we predicted, the positions that we projected at each point in time based off the average velocity of the collected data. As you can see, with the two slopes right there underneath the predicted data and collected data, the slopes are the same, and the collected data has a slightly smaller r-squared value because it is not as perfect as predicted data would be because of small human errors that I'll discuss in a minute. So the reasoning for the lack of change is explained by Newton's second law, because again, F equals ma. If acceleration is zero, velocity is constant, then F net must also equal zero. Because of course the object does indeed have mass, so that wouldn't be the reason that F net is zero. So the net force on the system, the rolling object, by everything else, which is the surroundings, ends up being zero, or canceling out in order to be zero total, because force does have a direction. For the chosen object we picked, as you can see over here, it doesn't have a lot of contact with the table. Can't really tell if you can see that from here, but just the two ends of it have contact with the table to help reduce friction. But friction isn't completely prevented because it's not a perfect world. So as you can see here, the r-squared value for collected data isn't perfect like the predicted data is. For the code, we took the mass of the ball on a scale, then we took the collected initial position and initial velocity from the tracker, and then we saw for line 49, I took how long it took for the object to get to the end and made that the ending while loop condition. F net down at line 54 is zero because, as again we discussed earlier, the net forces cancel out because in order to make velocity constant. So line 58 ends up using Newton's second law to not update velocity because velocity stays the same the entire time. Line 60 uses the position update formula, where the first position you can see right there is the final position, the next one is initial position, and then velocity times change in time is what updates position. So for the discussions and conclusions, if the axes were flipped, the velocity would change from negative to positive because it would be going in the positive direction instead of the negative direction. But the overall speed, which is magnitude of velocity, would not change because, again, the magnitude wouldn't change, just the direction of it would, because the velocity is made up of both magnitude and direction. We can tell that the net forces add up to zero, as we discussed earlier, and using general physics knowledge, we can tell, of course, gravity is going to be acting on it, then a force must be existing to counteract gravity, likely the normal force, and then however, we have some uncertainty with what other potential forces could be acting on each other to cancel out that we don't end up seeing. So we can predict some of the forces, however, we can't say with any certainty all of the forces. Thank you for watching.